Hi, welcome to AP Chem Speed Review, our third unit. We're going to be talking about intermolecular forces and properties, and Unit 3 is more heavily weighted than some of the others. We looked at the others and they were about 10% each of the exam, but Unit 3 is about 20% of the AP exam, so this is a more critical section. Here's all the little details, the fine print, but if it's too long, you didn't want to read it, it's all about intermolecular forces, IMFs. So we're going to look at the relative strength of various intermolecular forces. We're going to examine the forces when the molecules are the same and when they're different. Let's start with London dispersion forces. Now, these are the result of Coulombic interactions, and this is the temporary dipoles. So it's a temporary fluctuating dipole when two atoms or molecules move together and their electron clouds interact. Here's a static view of this. So if you have two helium atoms moving together, they each have two electrons. Well, they're not always, perfectly symmetrical around the atom. So let's say these move together. These two are more on this side. They're going to repel or push the electrons in this other helium away from them. And that's going to create a partial positive charge on this side of this atom and a partial negative charge on this atom. And therefore, they're going to attract each other slightly. So even though they are nonpolar, there's a temporary displacement as the electrons shift, and that creates this temporary induced dipole. Here is a moving picture of it. As you can see, as this gets closer, you begin to have this displacement of electrons, and that displacement creates this temporary positive-negative charge. So now, though weak, London dispersion forces are often the strongest net intermolecular force between large molecules, and that's important to remember. The LDFs are themselves the weakest of the intermolecular forces, but their net total can be quite large. So if you add up enough pennies, you can get a very large sum. In the same way, if you have a large enough molecule, the LDFs can be the strong force. Now, London dispersion forces are going to increase with increasing contact area between the molecules. That makes sense, right? As they have more ways to interact, you're going to have more electron cloud interaction. They will also increase with increasing polarizability of the molecules. So if the molecules are more easily, if there's more electrons to shift back and forth, it will create those temporary dipoles, those temporary attractions. Obviously, the polarizability increases with the number of electrons available and the size of the electron cloud. More electrons, bigger cloud, more polarizability. Also, interestingly, it's enhanced by the presence of pi bonds, which, as we know from the last unit, are double bonds. So all of those increase the polarizability of a molecule, and so thus the effectiveness of London dispersion forces. It's important to remember that London dispersion forces should not be used synonymously with the term van der Waals forces, which is the term I learned years ago. We're not going to use that. London dispersion forces is the preferred nomenclature. Now, the dipole moment of a polar molecule, that is the overall net charge of a molecule. This can lead to additional interactions. So remember, when we are looking at molecules' polarity, we add up, so we look at the more electronegative elements, atoms. In this case, we know that chlorine is much more electronegative than hydrogen, and so it's going to pull the electrons closer to itself, leading to a net negative charge on this part of the molecule and a net positive charge on this part of the molecule. And we call that a net dipole moment, if there's a net charge in one direction or the other of the molecule. Now we can look at dipole-induced dipole interactions, and this happens when there is a polar molecule, so a molecule with a permanent dipole, and a nonpolar molecule. again, that polar molecule can induce a temporary movement of the electrons and then an attraction in the nonpolar molecule. Those forces are always attractive. And of course, this attractive force is going to increase if the dipole is stronger and if the other molecule is more polarizable. There's more electrons to push and pull around. So here is an example of a dipole-induced dipole interaction. So here is the permanent dipole in this polar molecule, and it's going to induce a dipole in the opposite orientation in the nonpolar molecule. So this negative side of the polar molecule is going to induce a positive charge here and a negative here, and vice versa here. The positive side is going to induce a negative charge and a positive. So these permanent dipoles will create temporary induced dipoles in their non-polar counterparts. We can also get dipole-dipole interactions, and this is when we have two polar molecules, either the same molecule or different, but they're both polar. And again, the interaction is going to depend on the magnitude of the dipole and their relative orientation to each other. So let's look at HCl, which is a polar molecule, and these are going to orient themselves so that their opposite charges are close to each other. And so the negative part of this Cl will orient itself towards the partial positive charge of this H. Interactions between polar molecules are typically greater than those between nonpolar molecules of comparable size, because these are in addition to LDFs. Every molecule has London dispersion forces, polar, nonpolar. But so in addition to LDFs, these polar molecules with their dipole-induced or their dipole-dipole interactions create an additional attraction. So just here's another representation of this. Dipole-dipole molecules are attracted to each other, and they orient themselves to maximize the forces of attraction. A third kind of attraction is known as ion dipole attraction, and these are present between ions and polar molecules, and these are stronger yet. They're stronger than the dipole-dipole forces. So, for example, here is sodium chloride, salt, being dissolved in water, and the water molecules, which are polar, are going to orient themselves around these ions. So the positive side of the water molecule, the hydrogen side, is going to orient themselves around the negative ion. And here, the negative side, the oxygen of the water molecule is going to orient themselves around this sodium. And so you're going to see there's the sum total of this attraction of these partial negatives to this positive charge and these partial positives to this negative charge overall is a very strong attraction. So that's why this ion dipole interaction is stronger than just dipole-dipole. A fourth kind of bonding is known as hydrogen bonding, and this is a species of dipole-dipole bonding that pertains to hydrogen. Hydrogen is very small, and when it bonds to a highly electronegative atom like nitrogen, oxygen, fluorine, it allows the positive hydrogen or the partial positive of the hydrogen to be attracted to the negative end of the dipole, and because NO and F are relatively small, the hydrogens can get very, very close to those electronegative atoms, and that forms a very strong kind of dipole-dipole bonding that we identify as hydrogen bonding. So here's an example of it. So this is the electronegative atom, right? The oxygen and the nitrogen. This makes a partial positive on the hydrogen, and that hydrogen can get very, very close to this nitrogen, and that proximity creates a strong intermolecular attraction known as a hydrogen bond. It's not a covalent bond. The covalent bonds are here, but there's a hydrogen to electronegative bond there known as a hydrogen You can get these between molecules that are different, in this case, or between molecules that are the same. So we have hydrogen bonding that occurs between molecules of water. Right? The partial positive of this hydrogen can get very, very close to the negative charge of this oxygen. And this creates a strong bond. So let's just look at the types of bonds in a table here. The weakest strength of attraction here, the London dispersion forces, creates temporary dipoles, occurs between nonpolar molecules. It has a minimal effect on boiling point, but a pretty big effect on depressing freezing point. Then we have, we're skipping one that's the dipole induced, but that is occurs between a permanent dipole and a nonpolar. Here's dipole-dipole between two polar molecules. Its strength of attraction is greater than the London dispersion forces. You can see it has a moderate effect on elevating boiling point and a larger effect on depressing freezing point. Hydrogen bonding, which is a specific kind of dipole-dipole bonding, is higher than the dipole-dipole. It has a larger effect on boiling point and a more moderate effect on decreasing freezing point. And then finally, the ion dipole occurs between polar molecules and an ion, and that strength of attraction is quite high, and it results in a very high elevation of boiling point and a moderate or low depression of freezing point. So to put it all together, here's everything we've talked about. Going from weakest intermolecular force to strongest, although remember the overall effect on a big molecule of London dispersion forces can make it the overall net strongest attraction. So London dispersion forces temporarily induce dipoles, dipole-induced dipole, where a dipole creates a temporary attraction with a nonpolar molecule. Dipole-dipole, the interaction between two polar molecules. Hydrogen bonding, a special category of dipole-dipole, where the hydrogen can get very, very close to an electronegative atom. And then finally, ion dipole. In large biomolecules, the non-covalent interactions, they can occur between different molecules or between different regions of the same molecule. Because it's so big, it can fold around and begin to interact with other portions of itself of the same molecule. So you see this with proteins and carbohydrates and nucleic acids. In biochemistry, this is very, very important. And in fact, the structure and the shape of a protein is wildly influenced by this non-covalent interaction. And the shape and structure of these large molecules give them their organic function. That takes us to our second topic, properties of solids. So we can use intermolecular forces to explain the physical properties of a material. So our goal is to look at the macroscopic properties, and we're going to look at particulate level structures and the interaction of the particles. So many properties of liquids and solids can be determined by the strengths and the types of the IMFs. We know that when something vaporizes, right, the intermolecular interactions are actually broken apart. And so the molecules are allowed to separate. And so this will influence vapor pressure and boiling point. And those two things are going to be directly related to the strength of the IMFs. So if there's a lot of attractive forces, a lot of IMFs, then you're going to have a very low vapor pressure because the molecules are going to have a tough time breaking away from one another. Likewise, the boiling point is going to go up because it's going to take more and more energy to pull those molecules apart because of these IMFs, these intermolecular attractions. Melting points also tend to correlate with interaction strength, but because melting points are simply a rearrangement rather than a breaking away as in vaporization, the relationships are a little more subtle, so it's not quite as obvious. So we can use these particulate level representations to show some of these interactions. So this is what you see in a particulate level model. This would be a model of a solid where everything is really, really tightly packed together. And as you can see, this is probably an interstitial alloy because we have some extra smaller atoms in these interstitial spaces. Here would be a representation, a particle representation of a liquid, although probably this is a little more space than we would likely see in a real liquid. In a liquid, the molecules are still essentially touching, though they can slip and slide past each other. They're essentially in close contact. And this would be a particle representation of gas with lots and lots of volume between the individual particles. So we can represent elements with these particles, these diagrams, and the AP exam tends to use several of these. They like this particle representation stuff. So here's the way we would represent an element. Here's a diatomic element. Here would be a mixture, right? And these different colors represent the different atoms. So here's a mixture of single atoms and then diatomic molecules. So anyway, these are mixtures, these are compounds. So you'll see these represented this way. Ionic solids, remember, an ionic solid is not a molecule. It's not just one sodium and one chloride. It is the ratio of all the parts, and there's a 1-to-1 ratio. But an ionic solid forms this crystalline array, this lattice, rigid lattice network. And because of the very strong interactions between the positive and negative charges on the ions, ionic solids tend to have very low vapor pressures. They tend to stay clumped together. High melting points, takes a lot of energy to break them apart, and high boiling points. They tend to be brittle due to the repulsion of like charges. As we see, normally they're arranged to maximize attraction and minimize repulsion, but if you shift one layer with respect to the other, then the forces of attraction become forces of repulsion, and you'll have a cleavage plane. So they will tend to be brittle if you slip them, and that they'll pop apart. Ionic solids conduct electricity only when the ions are mobile. This is key. So if the ionic solid is melted, or if it's dissolved in water, then the ions are free to move, and therefore they can conduct electricity. Otherwise, they are locked together in this rigid structure, and they will not conduct electricity. So here it is representationally. When they're in their lattice network, in their solid form, the pluses and the minuses are locked together. Only when they are in solution or melted, so if you have molten salt, very, very hot, then it can conduct electricity. Or if you dissolve salt in water, then it will conduct electricity. But solid salt in the crystalline compound, it won't. We can also have what are known as covalent network solids. So it's not just ions and ionic compounds that form these networks. You can also have them with covalent bonds. And diamond is an example. It's formed by carbon, pure carbon, but it forms this repeating tetrahedron, and this forms a very large network of covalent bonds. And this 3D network, or in the case of graphite, a two-dimensional network, is very, very stable. So in diamond, it's in all three dimensions. In graphite, you have these strong covalent bonds that create this rigid structure in 2 dimensions, but then there are weaker forces that bond these planes together. And because of that, the graphite planes can slip with respect to one another very easily. Not so in diamond. Diamond is very rigid. And this makes graphite a great lubricant for locks and keys and that sort of thing. These network covalent solids are only formed from nonmetals, and they can be elemental, as we saw in diamond and graphite, or binary compounds made up of 2 nonmetals. So silicon dioxide, for example, and silicon carbide. Due to the strong covalent interactions, covalent network solids have high melting points, kind of like ionic solids. Their 3-dimensional networks are rigid and hard, and so and that's because the bond angles are fixed. But this is, like I mentioned, graphite's a little different. It can slip and slide. All right, so that takes us to molecular solids. Most molecular solids, now this is, remember, this is this network this network solid is this very particular kind of covalent solid. Most covalent molecules, most molecular solids are made up of covalently bonded molecules, single units that are attracted to each other through relatively weak intermolecular forces. And because of that, they are not going to be as rigid, they're not going to have as high melting points and boiling points. So their interaction is going to be much, much weaker than, for the example, that of an ionic solid. This ionic solid is held together with these strong electrostatic attractions, whereas this molecular solid is only held together by the weak interaction of the intermolecular forces, the London dispersion forces, and dipole-dipole if they exist, and hydrogen bonding if that exists. So this is the key difference between ionic solids and molecular solids. Molecular solids generally and therefore have a low melting point because of the relatively weak IMFs. They don't conduct electricity because the valence electrons in a molecular molecule, they're held within the covalent bonds and within the lone pairs of each molecule. So they're not free. They're rigidly accounted for within the covalent bonds. And so remember, in order to conduct electricity, electrons have to be free to move around. And so in molecules, they're not. So molecular solids tend not to conduct electricity. Molecular solids can be composed of very large molecules or repeating molecules known as polymers. Here is a giant molecule, one molecule. Polymers, the definition of it is a large molecule made up of hundreds of what are known as monomers that join together. So polymer means many, and mer means parts. So it's something made out of many parts. So for example, polyethylene is made up of thousands of ethylenes joined together, like beads in a pearl necklace or something. All right, that takes us to metallic solids. Now these we're much more familiar with, right? This is steel and copper and aluminum. Metallic solids are held together by a high density of shared delocalized electrons. We call this the sea of electrons. It's like metals are ions, like surrounded by a delocalized sea of electrons. But that delocalized sea allows these electrons to float around, make some great conductors of electricity. So there's still a bond there. It's called a metallic bond, but it's made up essentially of a positively charged nucleus and this sea of surrounding electrons. Metallic solids are characterized by high melting points. They can be soft and malleable, or they can be very hard. They are almost always good conductors of electricity because that sea of electrons allows them to move freely. They're free agents. Not only are they good conductors of electricity, they're good conductors of heat. They tend to be malleable. That means you can deform them, you can bend them. They tend to be ductile. That means you can draw them into a thin wire because you can rearrange those metal cores. They don't care. The metal cores can shift around, and then they just take as much of the electron cloud as they need to balance out. In an interstitial alloy, the interstitial atoms tend to make the lattice more rigid, and so many alloys have decreased malleability and ductility because they're just not as free to move as they were before the interstitial atoms showed up. But they typically retain their sea of mobile electrons and so may remain great conductors. Going back to large biomolecules, again, non-covalent interactions can occur between these big molecules or different regions of the same giant molecule. And the functionality and properties are extremely influenced by the shape of the molecule. And that shape is driven by these non-covalent interactions. So here's the relationship between a very small molecule, acetylcholine, and its and the specific interaction with a very large molecule, acetylcholine esterase. And anyway, so this gets us into biochemistry, organic chemistry, but yeah, this relationship is determined. The folding and the function of these proteins are determined by these non-covalent interactions. Now, if we look at a graph of the potential energy versus the distance between atoms, it's a useful way of describing atom interaction. We've seen this before in the previous unit, where the potential energy is dependent on how close these two atoms are to each other. So imagine this is like an energy hill, right? It's going to go from no energy, and it's going to gain energy release energy as it rolls downhill. And so this is the releasing of the potential energy as these molecules get closer together. So when they're relatively far apart, there's very little potential energy that can be released. But as they get closer and closer together, as they begin to attract each other, it can release this potential energy until it reaches this sweet spot. And this Goldilocks zone gives us the equilibrium between bond length and potential energy. If the molecules get any closer, then it's going to take energy to overcome the repulsive forces. So basically this lets us know what the bond energy is. This is the energy that's released as two molecules slam together, or it's the energy it would take to pull those two molecules back apart and separate them. Remember that equilibrium bond length is where the potential energy is at its lowest and the thing is at its most energetically stable. So low potential energy is associated with bond stability. All right, next topic, solids, liquids, and gases. And this is going to be a quick review of general chemistry stuff, but we're going to apply the notion of intermolecular forces to the macro properties that we already know from general chemistry. We remember that matter exists in three states, solid, liquid, or gas, and those differences are influenced by the spacing and the motion and the energy of the molecules. So we look at a solid, we know it has a rigid shape. It's a rigid structure. So all the parts, they don't move with respect to each other. That gives it a fixed shape, a fixed volume, and it's incompressible. It can't be squished. By contrast, liquids are not rigid, so their particles can move with respect to each other. Therefore, it does not have a fixed shape. But it does, like a solid, have a fixed volume, and like a solid, it can't be squished. And we're going to see that liquids kind of they're a middle ground between solids and gases. They have some properties like that of a gas. Notice how a liquid is not rigid like a gas. It has no fixed shape like a gas, but it has a fixed volume like a solid, and it has incompressibility like a solid. Gases, no rigidity, all the particles are free to move, no fixed shape, no fixed volume, and it can be squished. They can be compressed into very small volumes. Solids can be crystalline, that is arranged in a regular repeating three-dimensional structure, or they can be amorphous, which just means without a shape, a repeating shape. So they don't have a regular repeating orderly arrangement. An example would be rubber tires, or plastic, or glass. Those would be examples of amorphous structures. But crystalline structures would be something like salt or sugar. Okay, so yeah, salt, diamonds, these are crystalline solids. Plastic and glass, they're amorphous solids. Again, these have a repeating structure, whereas these are more amorphous. They're still packed closely together, but they just don't have a fixed geometry that we can identify. In both cases, the motion of the individual particles is limited. That is, they don't move with respect to each other. They stay relatively rigid. But as we're going to see with kinetic molecular theory, everything moves, including rigid structures. They don't move with respect to each other, but they vibrate and twist and stretch in place. So in a crystalline solid, the atoms vibrate in place in a fixed pattern. In an amorphous solid, they vibrate in place more randomly. The structure of the solid is influenced by the interparticle interactions and the ability of the particles to pack together. So the particles in a liquid are still, though they can slip and slide, they're still in very close contact with each other. Even as they move and collide, they stay tightly connected. Here's kind of a particle representation of that. Again, they can twist and slip and slide and move, but they never get very far apart. That's why they remain incompressible. So the arrangement and movement of the particles are influenced by the nature and the strength of the forces. So the polarity of the molecules, the hydrogen bonding that may be occurring, the temperature, which influences the movement of the particles. Solid and liquid phases for a particular substance typically have similar molar volume. So why? Because they both the solid and the liquid, the particles remain very, very closely connected to each other, in close contact. Even though the liquids move and the solids are held in place, they're still very dense. And that density, that close contact, gives them the incompressibility. And so essentially, they have the same molar volume. If you have a mole of each, they're going to take up about the same amount of volume because they're so tightly packed. This is very different from a gas, which of course the particles are very, very far apart. In a gas, the particles are in constant motion, and the collision frequency and their spacing is dependent on the temperature and the pressure and the volume, and that gives us all of our fun gas laws. Because of this constant motion and the minimal forces between particles, a gas has no definite volume. So nothing is clumping it together, so it's free to expand to fill the space. And it has no definite shape because, again, nothing is constraining it. So a gas in this constant motion with nothing to pull it together is just going to go everywhere and take the shape and volume of whatever its container is. Okay, this takes us to the ideal gas law. PV equals nRT. Pressure volume equals the number of moles times R, our universal gas constant, and times temperature. We're going to look at gas properties both at a macroscopic level using our relationships of pressure, volume, temperature, moles, that stuff, the gas laws, and we're going to look at it molecularly by looking at the motion of the gas. So the macroscopic properties of ideal gases are related to the ideal gas law, Pivnert. And the ideal gas law combines the four basic gas laws that we know: Boyle's law, Charles's law, Gay-Lussig's law, Avogadro's law. And it's just keeping track, right? We keep track of pressure in kilopascals or atmospheres. That's going to determine which of these two values of R we're going to use. Remember, if you use kilopascals, you're going to use the one that has the kPa's. If you use atmospheres, you're going to use the R value of atmospheres. Volume is in liters, moles are in moles, temperature is in Kelvin. Always remember that. Temperature calculations with the universal gas law are always in Kelvin. In a sample containing a mixture of ideal gases, the pressure exerted by each of the individual gases, the partial pressure of it, is independent of the other components. And so the total pressure is going to be the sum of the individual partial pressures. This is known as Dalton's law. So the total pressure is the sum of each individual gas. So let's say you have a combination of oxygen and nitrogen and hydrogen. The pressure of the oxygen by itself, without, apart from the influence of these others, plus the pressure of nitrogen by itself and hydrogen by itself, whatever, add them all together and you get the total pressure of the combined gases. The mole fraction that's the number of moles of one component in the total mixture, is going to be the same as the partial pressure fraction or ratio. And here's the math on that, but just rest assured, you know, the molar fraction is going to be the same as the partial pressure fraction. Kinetic molecular theory, KMT. We're going to apply this to both particle motion and macroscopic properties. So remember, kinetic molecular theory says that everything is in motion. Everything is in motion. Gases, liquids, solids. We use something known as the Maxwell-Boltzmann distribution curve to describe the distribution of kinetic energies of particles at a given temperature. So this is what this looks like, and this is a very common graph. You're going to see these and have to interpret these. So if we look at the fraction of molecules on this axis and increasing kinetic energy on this axis, what we see is that at a lower temperature, that's this blue line, a greater fraction of the molecules have a lower average kinetic energy. Now remember, some molecules are going to have very close to zero. Some molecules are going to have a high, but we're talking about the overall average. And the overall average at lower temperature is that a greater fraction are going to have a lower kinetic energy. As we increase temperature, it's going to shift the graph to the right. And since we're talking about the same number of particles, right, the graph is going to have to get lower because it sweeps out the same amount of volume. But so it's going to get lower, but it's going to shift to the right to show that an increasing number, basically, so the overall average of kinetic energy is going to increase. And if we pick some arbitrary threshold here, say the activation energy of a reaction or boiling temperature or something, we're going to see that as we shift the temperature, the number of particles that have sufficient energy to overcome some threshold is going to be increased at higher temperatures. So that's a Maxwell-Boltzmann distribution curve. KMT says all the particles in a sample of matter, any kind of matter, are in continuous random motion. Now we know this is true of a gas, but it's also true of a liquid, which while it slips and slides is wiggling and wobbling, and also true of a rigidly fixed solid. Those particles are still in constant random motion. They can't break away from each other, but they can vibrate in place, and they can twist, and they can stretch, and all that's happening. So the average kinetic energy of a particle is related to its average velocity by this equation. This is from physics. The kinetic energy is equal to 1/2 of the mass times the square of the speed, 1/2 mv squared. The temperature in Kelvin of any sample of matter is proportional to the average kinetic energy of the particles in the sample. So if we double the Kelvin temperature from, say, Kelvin 100 to Kelvin 200, we're going to double the average kinetic energy. So there's a direct proportion between temperature and average kinetic energy. Now let's look at deviations from the ideal gas law. Remember, what is an ideal gas? Well, it's a gas that will not condense at low temperatures. It's a gas that has no forces of attraction or repulsion between the particles. They are particles that have no volume. So obviously, an ideal gas does not exist. But at standard temperature and pressure, we get pretty close estimates when we look at real gases. They're fairly close to ideal. So the ideal gas law does not explain the actual behavior of real gases. And so these deviations result from interparticle attractions among gas molecules, remember, which they're assumed not to have, particularly at conditions close to those resulting in condensation. This is an important concept. So this will help you remember when gases behave close to ideal and when they do not. They behave less than ideal when they are close to condensation conditions. I'll explain that. Deviations can also rise from particle volumes. Right? Remember, ideal gas law assumes that they have no volume. But at extremely high pressures, those volumes begin to exert themselves. So gases are likely to behave ideally at high temperatures and low pressures. And it's better if they're small nonpolar molecules. They are likely to not behave ideally at low temperatures. That's when they're going to become closer to condensing. And if they condense, right, it's because they have attracted themselves to the point that they are now coming out of gas and into a liquid or a solid. And high pressure, well, high pressure is going to push the particles closer together, and since they do have a finite volume, it's going to manifest that. You can't infinitely compress gas as you could if it had zero volume. So at low temperatures close to condensation and high pressures, which reveal the existence of real volume, gases are not going to behave ideally. And of course, this is going to be made worse if they are large and polar molecules. So just remember that idea of condensation. That's when the attraction overwhelms and comes out of gas. And high pressure. That's the least ideal conditions. Okay, solutions and mixtures. We're going to talk about how IMFs influence solubility and separation of mixtures. It allows us to calculate the particles, the volume, and the molarity of solutions. Now, solutions, which are very important in chemistry, they are often called homogeneous mixtures, and they can be solids, liquids, or gases. And essentially, a solution is a combination of a solute, which is something that's going to be dissolved, and a solvent, which is what the solute is dissolved into. And the combination gives us a solution. So something dissolved, something to dissolve in gives us a solution. Every part of the solution is going to be like every other part of the solution. It's going to be what we call homogeneous. They don't vary. The macroscopic properties do not vary throughout the sample. And this is different from a heterogeneous mixture, where the macroscopic properties do vary depending on their location. So here's the classic examples of heterogeneous mixtures: chocolate chip cookies, right? Chunks of pizza, ice within a soda, salad. We express solution composition and solution concentration in molarity. So we express molarity as moles of solute, that's whatever has been dissolved, per liter of the entire solution. And we use a capital M for this. Molarity equals moles per liter. So this takes us to our molarity and dilution equation. M1V1 equals M2V2. If we dilute a solution, let's say that something's dissolved in water, and we simply add more water, that's going to leave the amount of whatever's dissolved unchanged. So if we had 1 mole of solute before dilution, we still have 1 mole of solute after the dilution. We've just changed the volume. But the moles stay the same, and since moles are calculated by molarity times volume, and they stay the same, therefore the molarity times volume of the initial condition is the same as the molarity times the volume of the final condition, or simply M1V1 equals M2V2. So this allows us to calculate how much volume we need if we want to change molarity. If we start with a high concentration of something, we want to get a smaller concentration of something, we can use this formula to figure out how much of the solvent we need to add to reduce our concentration. So we'll often use this in chemistry when we start with a stock solution, something with a very high molar concentration, and we need to dilute it to a lower molarity. Well, we'll just use this M1V1 equals M2V2 equation. We can also use this to calculate titrations when we try to figure out how much acid is going to react with how much base. So this is a very useful equation, M1V1 equals M2V2. Now that takes us to representations of solutions. And we're going to use, again, our old friend, the particulate model for mixtures to represent interactions and concentrations. So this is how this will work practically. You'll see a diagram like this, and you'll go to the legend here and look at this. And so HCl is an acid, and we know that it's a strong acid. It's going to dissociate 100%. NaOH is a strong base. It's going to dissociate 100% as well. Here is hydronium, which is how the AP likes to refer to hydrogen. So remember, the presence of hydronium is indicative of an acid. And then this is good old-fashioned water. So over here, what we have in beaker A, if we look at our thing, is we have taken some HCl, and that HCl has disassociated, right? So the Cl's now are just, they're going to be neutral ions, spectator ions, not neutral, but spectator ions. And we see the formation of these hydronium molecules. So this right here is a beaker of acid. It has hydrochloric acid in it. And we've added 0 base. Okay, so this is just acid by itself. Now we've added some NaOH. And now the base is going to dissociate, right? That's going to dissociate. And now you're going to see that interacting with the hydronium and reducing it to water. So notice that we start here with 4 hydronium molecules, and now we only have 2. So the base has interacted with some of our hydronium and reduced it to water. That's what happens when acids interact with bases. Acid plus base creates water. But we still have some. So we still have some acid. So here we have a strong acid. Here we have a weaker acid, but there's still the presence of hydronium. Here we're adding more base, right? And now look, no hydronium. So now we have it's been neutralized. We have neutralized all of our acid with our base. And so this would be an equilibrium point. And if we keep adding base, we're going to see that we're going to have free OH floating around. And that indicates that we now have a basic solution. So we've gone from a strong acid to a weak acid to a neutral to a basic solution. Okay, and that's all represented here in this particle model. Okay, now let's talk about separating solutions and mixtures using chromatography. The components of a liquid solution cannot be separated by filtration, right? If you try to take if you put liquid into a filter, if the filter lets any of the liquid through, then it's going to let all the liquid through. So we can't use filtration to separate liquid solutions, but there are other processes we can use that take advantage of the differences in the intermolecular interactions. And so there's a couple of things we can use. One is known as chromatography. Another is known as distillation. Chromatography can be paper chromatography, thin layer column chromatography, and it separates chemical species by taking advantage of the differential attraction of molecules to different parts of the solution. So basically, we have a mobile phase, something that is moving through the paper or the column, and then something that isn't moving. This is more evident when you look at actual chromatography. So let's say we take a spot of black ink on a piece of paper, and we dip that paper into water, and the water is going to wick its way up this paper. As it does, it's going to take some of this ink with it, and that's the mobile phase. As the water moves up the paper, which is the stationary phase, this ink is going to be differentially attracted to the paper at some point. So some parts of it will be attracted earlier than others. So the yellow is going to stay in the mobile phase. It's going to travel with the water the longest. And these other colors are going to peel off as they find the place in the stationary phase where they're more attracted to the paper than they are to the solvent, the water. And so we separate this. This looks like, hey, how can I separate the different colors of this ink? We can do this with chromatography. So here's another example of this being separated. Another example. Here is a column where we're doing the same thing. So the other process we can use is called distillation. And again, it takes advantage of the differences in vapor pressure. So, for example, if I have a mixture of water and alcohol, and I want to increase the concentration of my alcohol and leave the water behind, I will use this distillation apparatus. And because there's a difference in boiling point, since alcohol boils earlier than water, the alcohol will come off earlier, and then I can condense it, and then I can have more concentrated alcohol here and leave the water behind. This is what the old moonshiners would do. They would use this process of distillation to concentrate alcohol. Here is a lab setup. All right, that takes us to the topic of solubility. Solubility means dissolvability, whether things will dissolve into one another. And again, this is determined by the intermolecular interactions between the particles. Substances with similar intermolecular interactions tend to be miscible, which is just a fancy word for soluble in one another. There's an old saying, like dissolves like, so polar molecules will dissolve other polar molecules. So ethanol and water dissolve in each other because both are polar. And nonpolar things will dissolve nonpolar things. So hexane and oil are nonpolar, and both will dissolve into each other. But nonpolar will not dissolve with polar. So oil and water, nonpolar and polar, will not mix. You've heard that saying your whole life. Oil and water don't mix. Here's why. Because we're trying to combine a nonpolar with a polar molecule, and it doesn't happen. So you can pour them together, but they'll separate out because they don't want to be, they're not like each other, therefore they will not dissolve each other. All right, that takes us to spectroscopy and the electromagnetic spectrum. Spectroscopy can determine the structure and the concentration of a chemical species in a mixture. So basically, it's the interaction between matter and electromagnetic radiation. And what we do is we bombard matter with electromagnetic radiation, and we look at the results, and those results will tell us what kind of atoms that we are dealing with. So basically, we're looking at the colors that come from bombarding something with electromagnetic energy. And we use all different bands of the electromagnetic spectrum. So we know that white light, for example, is made up of these other visible spectrum, these other visible wavelengths. But this is true of the entire electromagnetic spectrum. So we start over here with very, very long wavelengths, and they go to very, very, very short wavelengths. So things like radio waves and TV waves are very, very long. Microwaves are long. Infrared rays get shorter. And then we have here in the middle visible light. As you can see, visible light is only a thin section of the entire electromagnetic spectrum. As the rays get, as the wavelength gets smaller and smaller, we move into ultraviolet, X-ray, and then gamma rays. So we're going to explain the relationship between a region of the electromagnetic spectrum, we use these different regions, and the type of molecular or electron transitions that we see reflected from those regions. And this is due to the differences in absorption or emissions of photons, and this will be related to various movements of the molecules or the electrons. So microwave radiation is associated with transitions in molecular rotation levels. So here is an infrared spectrum of carbon monoxide, and you're just going to see this repeating pattern. We don't have to get into the math of it or anything, but basically this is caused by the rotation of that molecule. Infrared radiation is associated with transitions in molecular vibration levels. So you've got rotation and you've got vibration. So here is a spectrum of vibration rotation for HBr. Again, we don't need all the details here, but just we can see that if we bombard something with a particular EM radiation, we can start to see these effects, and we associate those with its vibration movement. Ultraviolet and visible radiation is associated with transitions in electronic energy. That's the energy of electrons. And putting these all together, you can start to see these repeating patterns. So we bombard some molecules with different wavelengths of light, wavelengths of radiation, and we're going to see big lines. These big red lines are going to be various visible light spectra that pop out. These blue lines are going to be vibrational indications, and these green lines are going to be rotational indications. And so we're going to see all of these different things that correspond to the different parts of the EM spectrum. This takes us to the photoelectric effect. So when we bombard matter with photons, with light, some of those photons are absorbed, and they can cause light to be re-emitted. So electrons can absorb photons and then be promoted, and then as they drop from a higher level back to a lower level, they'll re-emit, they'll transmit those photons. And that corresponds to this electronic transition, this movement of electrons from a lower to a higher level and back again. So when a photon is absorbed or emitted, the energy of the species is increased or decreased by the amount equal to the energy of the photon. So basically, here's the continuous spectrum of visible light. If we bombard some matter, you'll notice that what is reflected from that is you're going to see some pieces missing, because some of this energy gets absorbed by the electrons to promote them to a level, and then when they drop back down, then they will emit this spectrum, and you'll notice that the emitted light is the same as the missing pieces of the absorbed light. So this emission spectrum will correspond to a particular atom and its particular electron orbitals. So here again, we're just bombarding something with light rays. We get these electrons being kicked off, and we can keep track of that. And this is known as the photoelectric effect. So again, it has to be not every wavelength will work. So if we start with something with like these longer infrared, we don't get electrons kicked off. At some point, we start to get a few with visible and ultraviolet. With X-ray, we always get them. With gamma rays, even more so. So what we see here, we have this energy equation where the energy is related to what's known as Planck's constant times the frequency. We're going to see increased frequency is going to create greater energy. Well, here's the payoff. The payoff is that this atomic absorption and emission is very selective and specific for particular elements, and allows us to identify unknown elements by comparing them to known. So let's say we bombard an unknown sample, and we get this emission spectra from it. And we say, okay, well, what does this correspond to? Beryllium, no. Copper, no. Manganese, no. Strontium. Oh, it's exact. So we must have a sample of strontium. So these are like fingerprints. There are light emission fingerprints that identify the particular atom that we're dealing with. So this takes us to what is known as the wave equation. The wave equation relates the wavelength, which we call lambda, of the electromagnetic wave, to its frequency, which we call nu, and to the speed of light. So basically, in general, the velocity of a wave is equal to its frequency times its wavelength. Well, but since the speed of any wave in a vacuum is the speed of light, we can just say that the speed of light, c, is equal to lambda, the wavelength times the frequency. We keep track of frequency in per second. We keep track of wavelength in meters. And so we get this formula, right? the speed of light is equal to lambda times nu. The energy of a photon is also related to the frequency of the electromagnetic wave through Planck's equation, which we saw before, right? The higher your frequency, the more energy you have, which is why some forms of energy cause the photoelectric effect and some do not. You can combine those two equations in this way, and you'll need to be able to use this. This is on your AP equations and constants, but you'll need to be able to use and combine those two equations, the wave equation and Planck's equation. That takes us to Beer-Lambert law. This is all about absorption, light absorption. And the amount of light absorbed by a solution is related to the concentration of the solution, the path length, so how much distance the light has to cover, and what's known as molar absorptivity, how much light this solution will absorb. So this gives us the Beer-Lambert law, which relates the absorption of light by a solution to three variables. So it says the absorption is according to this equation, EBC. And this means our absorbance is equal to the molar absorptivity times your path length times your molar concentration. And so basically, right, we take some incoming light and we pass it through an absorbing sample. It has to travel a certain distance, and we just measure the difference between the incoming energy and what is left over after it goes through the sample. So here's the practical payoff here. The absorbance is, so usually they keep the path length the same, they keep the wavelength of light the same, and so what's left is that the absorbance is going to be proportional to the concentration of the absorbing molecules. So the amount of absorbed light is going to be proportional to the solution concentration. If we increase our molarity, if we increase our solution concentration, we will increase absorption. If we decrease our concentration, we'll decrease absorption. And we get a graph that looks like this. And here's the basic payoff. Basically, you can begin, so once you have this graph, and you can say, hey, this doesn't change. This tends to be the same slope, this line. So we've done it with these four standards. Well, that allows us to interpolate something in between those standards. So we can say, well, hey, what's the absorbance, say, at this particular concentration? Or what is the concentration at this particular absorbance? So we can determine the concentration of an unknown sample. So for example, if we just said, okay, well, what's the concentration, if our absorbance is 0.7, then what's the concentration in molarity of our solution? And we'd say, oh, well, it must be 23. Okay. And we're just finding, this meeting point. So that's how you would interpret a Beer's law plot. They'll give you absorbance, ask you for concentration, or give you concentration, and ask you for absorbance. Okay, key concepts. IMFs, ranking IMFs from lowest to highest. London dispersion forces are the lowest, although they can be the net greatest in large molecules. Dipole induced dipole, dipole-dipole, which happens with polar molecules. A particular kind of dipole-dipole interaction known as hydrogen bonding, which occurs when hydrogen is bonded to O, N, or F. And then finally, ion-dipole interaction, which is the strongest. High IMFs equal high boiling points. Ionic solids have high boiling points and high melting points because they must have very strong IMFs, which they do. They have that electrostatic charge. Also very strong are covalent network solids, which mimic the high boiling points and strength of some of the ionic solids. But in general, molecular solids have low IMFs, therefore much lower boiling points and so on. We talked about large polymers and large molecules, how they fold and interact with other parts of themselves. We contrast that to metallic solids, which are like ions surrounded by a delocalized sea of electrons. We talked about how IMFs influence liquids, solids, and gases, ideal gas law, Pivnert, Dalton's law, total pressure is the sum of the partial pressures, kinetic molecular theory, how temperature in Kelvin is directly proportional to average kinetic energy, what influences actual gas behavior, since gases actually do have volume and they do have slight attraction. Our molarity equation, chromatography as a way of separating mixtures, distillation as a way of separating mixtures, solubility, like dissolving like, spectroscopy using light to determine the identity of particular elements, the photoelectric effect, here's our energy and Planck equations, and Lambert Law, A equals EBC. Okay, that's it. Thank you so much for your time.